When you're trying to look for ways to get better at doing math, one of the things you have to keep in mind is that we oftentimes measure our success based off of how we do in quizzes or exams. And quizzes or exams aren't always necessarily the best way to measure how good we are at math. Oftentimes, we understand the ideas, we understand the principles, but we make mistakes, we lose track of small things. Something happens on the way. One thing to keep in mind is that a quiz or exam doesn't actually tell you so much how do you do at math. It says, how do you do at communicating your mathematical knowledge? There is no machine that we can do that directly measures your math ability, but there is ways that we can say, well, how well can you communicate your math knowledge? So oftentimes, people who aren't great at math but do a good job of communicating what they do know end up performing better than people who are good at math but don't do a good job. So you want to work on ways of practicing communication. And oftentimes, if you talk with people about math and how you understand things, what you think should work, what you think should not work, you'll find that it helps you to identify gaps in your understanding. In other words, communicating ideas will help you tremendously. So how do you do it? Well, you need to learn to study in groups and take turns. Don't always be the quiet person taking notes. Be assertive. Say, hey, let me try one. Or here, let me do one. I want feedback. Make sure to ask lots of questions. You ask questions for other people, but also ask questions for yourself. What are you doing? Or perhaps, what are you doing? Depending upon the situation that you're in. See what's going on, and work on being organized. Organized answers, we love them when we're grading because it really helps us to follow the argument. The better organized an answer is, the easier it is for us to see what happened, which means more partial credit. And so, work on getting nice, clean answers. And it also helps because one of the things you should get into the habit of doing is checking your work. And if your work is all over the place, it's hard to check it. Now there's this last little piece down here. Now this is Chinese, and it's something like Jian Zhi Shui Jinan. What does it mean? Well, it means when you look, it seems easy. When you study it, it becomes hard. What it means is oftentimes when you see an instructor or another teacher, a student, somebody else doing it, the problems, they flow beautifully, like art. And so you think, oh, this is an easy thing to do. I don't need to practice. But then, once you get on a test, you find, why is it not flowing so well? Why is it so hard? Well, it's actually hard. It was always hard. When people make it look easy, it's because of a lot of practice. You too can get to that point, but not without doing lots of practice. So we're now ready to talk about today. Now our goal for today is to get better doing integrals which involve trigonometric functions. Now why do we care about that? Trigonometric functions are actually really important functions. The big idea here is that they're used to model periodic behavior. So if you have anything which repeats, then you can say, all right, I can approximate it by combinations of trigonometric functions. And we really truly mean anything that repeats. Even if it doesn't look like a trigonometric function, by combining trigonometric functions together in the right way, we can make them look like what we need them to do. Now there's another thing that happens in that oftentimes there's this interplay between algebra and trigonometry. So we might start with an algebra problem and transform it into a trigonometric problem. Well, if we do that, we need to get good at doing trigonometric integrals. We'll also see, in some cases today, where we'll take a trigonometric problem and turn it more into an algebraic problem. And again, to do that, we need to be able to handle the integrals. And so there's this beautiful play between these two fields, algebra and trigonometry. And that'll be a common theme this time as well as in our next session. Now, one of the big ideas that happen when you're working with trigonometric function is, what are the identities? Which ones do we need? The answer is you need 6. These 6 identities will get you through calculus 3. Now, there's a lot more than 6 identities, and it is true that there are obscure identities that people can always cook up. But in terms of what do you need to do well, the answer is, if you can do these well, then you're good to go. So let's walk through them. The first 2 are called the Pythagorean identities because they're the Pythagorean theorem just phrased in a different way. So a squared plus b squared equals c squared. So the one that most people know by heart, sine squared plus cosine squared equals 1. But an equivalent way is tangent squared plus 1 equals secant squared. And the way you get from the first one to the second one is divide everything by cosine squared. The next pair, these are called the double angle formulas. So if I have sine of twice an angle, that's 2 sine times cosine. If I have cosine of twice an angle, that's cosine squared minus sine squared. Why is this important? Well, it lets us take something that has a double angle and reduce it to something without. Occasionally we will go the other direction. Like, oh, here I see 2 sine cosine. I can simplify it to sine 2 theta. See, because this thing has 2 terms, this has 1. Half as many. And the fewer, the better. Cosine squared minus sine squared. Oh, I can make it cosine 2 theta. On a side note, cosine 2 theta actually has several different forms, because what you can do is you can combine sine squared plus cosine squared equals 1 to write cosine squared minus sine squared in different ways. For instance, I could replace sine squared by 1 minus cosine squared, and if we did that, we'd get 2 times cosine squared minus 1. And if you rearrange that, you get the last thing. You get what we call power reduction. Because we're going to replace cosine squared. See that square? That's tough. It's like you have 2 cosines together. Well, that's equivalent to 1 plus cosine of 2 theta over 2. See, we reduced our power by 2. Now, in the process, we added a plus sign in the middle. That's okay. We'll live with that. Sine squared, similarly, becomes 1 minus cosine 2 theta over 2. So these 6, you should know these by heart. Know when to use them. Know when not to use them. So we're going to work with these. So our goal is we're going to try a couple of different scenarios, work through them, and we'll see where we end up. All right. So let's start with the first type of integral that you'll see, and this will be probably one of the more common ones. Namely, if you have a power of sine times the power of cosine. So sine to the px, cosine to the qx. Now, there's some easy cases. Well, what are the easy cases? If p is odd, well, that says I have a single odd sign, and then I have a bunch of sine squareds. Now, why is that useful? Well, if I have a bunch of sine squareds, what happens is I can say, oh, sine squared becomes 1 minus cosine squared. So that allows us to write it in the form, lots of stuff involving cosine and a single sine, which means we can do a substitution. U equals cosine, life is good. Because remember, if I substitute u equals cosine of x, then we can say that du would be negative sine of x dx. So in other words, if I substitute a single cosine, u equals cosine, I just need one sine for the du. That's why p is odd is good, because we can make advantage of that. Similarly, if q is odd, well, what do? Well, we're going to pull off a single cosine to the side. Why? Because that single cosine becomes cosine x dx. That becomes part of our substitution. Everything else becomes part of sine. Okay, and so the nice case is, by making this nice substitution, life is good. Now the harder case is if they're both even. Well, if they're both even, power reduction. So you got to work down till you get something nice. So we'll start here. Find the integral of sine cubed of t cosine of t. Now we can do that. That's not so hard. Why? Well, we probably could have done this before we even thought about it, really. Because look, we have a single cosine t dt. Now that's suggestive. What is it suggesting? Well, it says, hey, let's make a substitution. U equals sine of t. And if we did that, we would get that du is cosine t dt. So the last part becomes our du. And now we have, lo and behold, this is u cubed, because sine cubed of t, remember the notation for trig, it's a little different. This is the same as saying sine of t cubed. So u cubed du. Well, that's 1/4 u to the fourth plus c, because we can integrate u cubed. And finally, we substitute back, because we have to we started with t, we have to end with t. So this becomes 1/4 sine to the fourth t plus c. All right, there you go. Now, at this point you could say, hey, couldn't we have done something differently? Because notice, they're both odd. All right, so let's try the other thing we could have done. So what's the other thing we could have done? Well, we could have said, let's write everything so that we have a single sign on the end. Now you might think, how do we do that? Well, so here we go, alternate. So we could do it in the following way. We'll pull off a single sign. So I have a sine squared t, cosine t, and a sine t dt. Now our goal is, once I have this on the end, that's going to become my du, possibly with a negative. So we say, okay, we want to rewrite this part to be just in terms of cosine. Is that possible? Well, yes, because we have our identity, which says sine squared plus cosine squared equals 1. So sine squared becomes 1 minus cosine squared. So 1 minus cosine squared t cosine t sine of t dt, which becomes, well, cosine t minus cosine cubed t times sine of t dt. Now we're ready for our substitution, because everything is in terms of cosine with a single sign at the very end, so that we could say u equals cosine of t, du equals minus sine t dt. So I'll move that minus across, and we get that this is cosine t becomes u, minus cosine cubed becomes minus u cubed, and sine t dt becomes a minus du. Well, we can move the minus in, so this becomes integral u cubed minus u du, which, well, that's 1/4 u to the fourth minus 1/2 u squared plus c. And now, what do? Well, now we come back, say u is cosine t. So it's 1/4 cosine to the fourth t minus 1/2 cosine squared t plus c. Now you might say, wait a second, that does not look like this answer. Are they the same? And the answer is, they are the same. Now it's not obvious that they're the same, and it takes a fair amount of work. But it is possible to show that yes, these in fact are equal to each other. And what's the moral here? Well, the moral is it is possible to do things in different ways. It's possible to have answers that look different, but in fact are really the same up to various constants. All right, so there we go. There's our alternate solution. So again, if either one is odd, you pull off one part of the odd part to the end, and then life is good. Make sure you use that sine squared plus cosine squared equals 1 to rewrite, and everything works out nicely. And we'll come back and revisit with another example later on. So don't worry, more to say about that. All right, well, that was the easier case. Let's do a harder one. sine squared t cosine to the fourth t dt. Now for this one, what do we do? Well, they're both even. So the problem is I can't pull off a single sine. If I tried to pull off a single sine, what would happen? Well, if we did that, let's see. That would give us a sine of t, a cosine to the fourth t, and a single sine. Now, here's the challenge. If I try to do a substitution now, say cosine, this part would become my du up to a sine, but I'd have to rewrite a single sine in terms of cosine. I can't do that. The reason I can't do that is because, well, I mean, we could do it. Okay, what's our problem? What was great here, but not great there? And the answer is, actually, let's go back to our other example we just did. The reason we had such a great time here was, see how you have a sine squared t right here? And you can replace it by 1 minus cosine squared. So what you really used was the even power, sine squared. So if I wanted to replace just sine, I'd have to introduce a square root of 1 minus cosine squared. And that's bad. Introducing square roots like that gets us into trouble, and we don't want to be in trouble. So that's why we don't pull off a single sine or a single cosine. It's just going to make things worse. So what do? Well, we say, all right, our problem is that both our powers are even numbers. So we're going to engage in power reduction. So again, you see both powers are even, and it's all sine and cosines. Power reduction. So where do we start? Well, the thing is, we want to reduce everything, the sine squared and the cosine squared. Now, we said there were 2 power reduction formulas. There are actually 3 power reduction formulas. Let's come back to our trig identities. So these 2 are power reduction formulas, cosine squared and sine squared. But you see this one up here, sine 2 theta? That also can become a power reduction formula if you think of it in the following way. I can take a sine times a cosine and replace it with sine of 2 theta over 2. Perfectly legal. Now, why do I point that out? Well, this is one of the things I like to do. So there's 3 power reductions. If it's just cosine squared, okay, if it's just sine squared, or if it's sine times cosine. Each one of them we reduce down to a smaller set of terms. So, let's come back here. What can we do? Well, here's what I would do. And again, multiple ways. Not always, there's more than one way to do it. You don't have to do it the exact way that I do it, but this is just one way to see it. And you should work on doing it in a way that makes sense to you. Now what I see is, whenever I see sines and cosines together, I like to do them together. So I'm going to think of this as sine t cosine t squared, and then I'm going to think of it as cosine squared t dt. So I'm just rewriting it. Now the sine t cosine t squared, I can replace the inside by power reduction. It will become 1/2 sine of twice the angle. The cosine squared t, well, that'll become 1 plus cosine 2t over 2. And of course, I should write that as squared, and there we go. So, again, this part right here, by power reduction formula, becomes that part down there. So, let's see what we have here. I have a half squared, then there's another half here, so I'm going to write that as 1/8. Now what? Well, I'm going to have sine squared 2t times 1 plus cosine 2t. And there we go, dt. So let's multiply this out. So we get 1/8 sine squared of 2t plus 1/8 sine squared of 2t cosine of 2t. and that's dt. Now notice something here. I want to point this out. Notice we have a plus here. Now when you see a plus like that, that says I can separate the problem into two parts, and I can handle the parts differently. I don't have to do it the same way for both parts. Now the reason I notice this is because if I look on the second part, I say, ooh, that looks really good. The insides match. Insides matching are good. And what else do we have? Well, we see a sine squared cosine. Well, that means we have a sine to an even, cosine to an odd. That's a good case. That's a great case. So the second integral we can do by substitution. In other words, if I think of this as integral 1/8 sine squared of 2t cosine of 2t dt, I want to think of this cosine 2t on the end as being my du, and we'll let u equal sine of 2t. Du would be 2 cosine 2t dt. I move that 2 across. Get a half du is cosine 2t dt. So what do we have? Well, we have the integral 1/8 times another 1/2, that's 1/16 u squared du. Well, 1/16 u squared, and it becomes 1/48 u cubed. Plus, of course, a c, which means that this part becomes 1/48. U was sine of 2t, so sine cubed of 2t plus c. All right, that's the first part. Now, sorry, that's the second part. It's just the part we actually worked out first. How do we handle this part? Well, if I think of this, what am I in? And remember, when you're doing integrals, whenever you update an integral, you should always say, let me think of it through fresh eyes. Okay? Forget where it came from. All I see is the integral that's in front of me right now. And that integral, I see, oh, it's sine to an even power, cosine to an even power as well. It's just cosine to the 0 power, which means power reduction. Reduce the power. All right, so how do we do that? Well, so this will become 1/8 for sine squared. It becomes 1 minus cosine. And now we have to do double the angle. Do you see it's currently 2? What's double that? 4t all over 2. Okay, so that's that integral. So I can think of this as the 1/8 and a half gives us 1/16. And now we integrate. Well, okay, so I got the 2 and the 8. Integral of 1 is t, because we're integrating dt. How about the integral of cosine? The integral of cosine is sine. Don't forget the minus. So sine of 4t. Anything else? Right. Don't forget. You have to compensate for the fact that there's a 4. How do you do it? Put a 1/4 in front. Plus c. So, if we multiply it through, we only need one constant. So what do we have? We have 1/16 t, 16th times a 4th, minus 1/64 sine of 4t plus that part, 1/48 sine cubed. And that's our answer. Life is good. Great. Good. So this is a power reduction formula. And this is sort of at the extreme of what we probably would want you to be able to do. There's lots of things you can be careful of. A common mistake, and I'll tell you that this is a mistake I have made in the past, which is why I know it's a very common mistake, is remember to double the inside. So if it's already a 2t, remember to double that to make it 4t. So you can't forget. Now you might say, do we have to go back and rewrite it in terms of just sine of t, cosine t? And the answer is not today, because there's no reason to. There will be situations when you do have to go back and write things in terms of sine t and cosine t. And should that situation arise, we have ways to do that. Essentially, the double angle formulas. If you use double angle formulas, you can get back in terms of sine t, cosine t. And as with almost anything involving trigonometry, oftentimes there's more than one way to manipulate the trig identities, which means that the answers can take multiple different forms. This is one form. That does not mean it's the only form. So if your answer looks slightly different, that doesn't mean you did it wrong. It just means you did it in a different way. And different isn't always worse. It's just different. So there you go. There you go. Okay, now let's do another one. Now, the following is a little bit less common, but we might as well mention it. And it's, suppose you encounter something of the following form. The square root of 1 plus or minus cosine theta, or 1 square root of 1 plus or minus sine theta. Now, what do we do here? Well, we want to get rid of the square root. That would be great. That's actually a huge theme that we have is get rid of the square root, or at least get down to something that we can work with. Now, there's a couple of ways you can do this. There's actually 2 bullet points, and these are not meant to be sequential. First do this, then do that. It means like if you're in the case of either case, square root of 1 plus or minus cosine, square root of 1 plus or minus sine, you can always multiply by the conjugate and then do substitution. If you're in the case of 1 plus cosine theta, 1 minus cosine theta, you can use power reduction, but do it in reverse. Now, there's a word of warning here. Don't forget about the absolute value sign. And what that is saying is whenever you take a square root of something, you're always tempted to say, oh, you just, drop the square root. And, well, let's actually get into the problem. And then we'll see why we need to say, don't forget about the absolute value sign. So there's 2 bullet points, which means we can do this in 2 different ways. Because this is a cosine. So let's see what we could do. We want to get rid of this square root. Now here's a cool thing. If I could rewrite this so that there was no plus, then life would be good. So in essence, sort of our sticking point is we want to get rid of the plus. If we could get rid of that plus, life would be great. So how do we get rid of the plus? Well, we're looking for trig identities. And our go-to trig identity with sines and cosines is the following one. Sine squared plus cosine squared equals 1. And why do I say that's our go-to? Well, notice if we could rewrite this not as 1 plus the cosine, but as 1 minus cosine squared, that would become sine squared. Now here's the cool thing. If I can somehow make this a 1 minus cosine squared, I can get it to look like a sine squared, and now I can get rid of the square root. So there is sort of an idea in play here. We just have to sort of follow through what this suggests. So let's think about what we can say. So we're going to multiply by the conjugate on the inside. Now when you do that, the reason why you multiply by conjugates is it essentially says, make things look like a squared minus b squared. So I'm going to think it says 1 plus cosine of 4x over 1, because I can always make anything look like a fraction. And I'm multiplying on the inside 1 minus cosine of 4x over 1 minus cosine of 4x. You might worry, should we ever worry about the fact that something might be 0? The short answer is not today. We'll talk more about this later on. All right, so we're doing that integral. So what do? Well, 0 to pi fourths. When you multiply the top, you're going to get the square root of 1 minus cosine squared 4x over the square root 1 minus cosine of 4x. All right, well, now what? Now is our chance to use this fact. This becomes the integral 0 to pi fourths of the square root of sine squared of 4x over the square root of 1 minus cosine of 4x. Now, square root of sine squared. Well, square root of sine squared is going to be, and here's the time you have to be careful, absolute value. Now the question is, do you need the absolute value? And the answer is, look where you're integrating from. we're going from 0 to pi fourths. So that means that our input that we're plugging into our sine function goes from 0 to pi. And if you're familiar with the sine function, sine is positive from 0 to pi, which means that, lo and behold, we can get rid of the absolute value sign. So this is just simply going to become sine of 4x. All right, so multiplying by the conjugate, lo and behold, what do we get to? We get to sine of 4x over the square root of 1 minus cosine of 4x. Now at this point, you're probably thinking, well, have we achieved anything? And the answer is, we have. Why? Well, go back to our old tools. Remember, whenever we do an integral, we can always think of, don't worry where it came from, what's the integral that we're faced with right now? And if you look at this integral is set up for substitution. Because if you let u be equal to 1 minus cosine of 4x, then du becomes what? Well, the 1 goes away. Derivative of cosine would be negative sine. I already have a negative, so that would make sine of 4x, then times 4 by chain rule dx. Oh, this times 4, move it across as 1/4. So, sine of 4x dx is 1/4. So what do we get? So this becomes integral. Upstairs we get 1/4. Then this is our du. And then what do we have? Square root of 1 minus cosine 4x. That's u to the minus 1/2. Right? Because square root of u, but downstairs. So minus. So we're just rewriting this in a very calculus-y way. Now we're not done yet. We need to figure out our bounds. Well, plug in 0. 1 minus 0, that's 0. Plug in pi fourths. Cosine of pi, because 4 times pi fourths is pi, is minus 1. 1 minus minus 1 is going to be 1 plus 1, also known as 2. So, what do we end up with? Well, we have 1/4, add 1 to the exponent, would give us 1/2, multiply by the reciprocal, so that would be 2 over 1, and evaluate from 0 to 2. Well, I can do a little bit of simplifying there, so I get 1/2 times u to the 1/2, evaluate at 2, which is square root of 2, and then plug in 0, you get 0. So we get 1/2 square root of 2, and that's the answer. All right, well, this one I said we could do in 2 different ways. So what's the other way? Let's work that other way through. The other way is the second bullet point, because this is the 1 plus cosine. Now, if it was 1 plus sine or 1 minus sine, out of luck, you got to do it multiplied by the conjugate. But here we can use our luck. Our luck is in our favor. So 1 plus cosine is twice cosine squared of 1/2 theta. So what do we have? We get integral of 0 to pi fourths square root 1 plus cosine 4x dx would be equal to integral 0 to pi fourths of square root of 2 times cosine squared of 1/2 this angle. So 1/2 of 4 would be 2. All right, well, square root of 2 is square root of 2. That's actually constant. Go ahead and pull it all the way out. So we have square root of 2, 0 to pi fourths. Now, square root of cosine squared. Square root of cosine squared would be, if we just looked at this little piece here, we want it to be absolute value of cosine 2x. But what do we need to check? Well, what's the sign? So we're going from 0 to pi fourths for x, which means what we plug in goes from 0 to pi halves. And cosine is positive there, which means this is a positive quantity, so we don't need the absolute value. So we actually can get rid of the absolute values. So this becomes 0 to pi fourths of cosine 2x dx. So we integrate cosine. If you integrate cosine, that'll give you sine of 2x, then multiply by a 1/2, and evaluate from 0 to pi fourths. When you plug in 0, Sine of 0 is 0. Plug in pi fourths. 2 times pi fourths is pi halves. Sine of pi halves is 1. So that means you're left with this piece in front, which is 1/2 square root of 2. All right, there you go. That's it. That's the two ways to do that one. Okay, well, there are, of course, other things which are not sine times cosine. So let's take a look at some of them. Okay, so our next one are secants and tangents. Now, the philosophy is very similar. So if you think about what we were doing when we had sines and cosines, it was like, well, let's set something up for a good substitution. So if we have some power of secant times some power of tangent, there's really 3 possibilities. And all these 3 possibilities are what can happen after you manipulate and rewrite your expressions. So one thing you could do is you could get some power of tangent and then a secant squared by itself. And what do you do in that case? Well, the secant squared, hey, that's the derivative of tangent. So this is setting up for u equals tangent of x. The other thing that could happen is you could get some power of secant times secant tangent. What's happening? Well, you're really substituting u equals secant of x. So you get some combinations of secants. It doesn't just have to be a single secant power. You get all sorts of stuff. But if you can get stuff involving secant times secant tangent, life is good. Now the last thing is you might get secant to an odd power. And what do? Well, a difficult journey lies ahead. And we'll take that journey in a few minutes. There are, I suppose, a few other things that you need to be aware of. You might have to know the integral of tangent, but we do. The integral of tangent is log secant. And of course you should know the integral of secant, which is log secant plus tangent. But using the identity tangent squared plus 1 equals secant squared, any integral that has this form can be reduced to one of these 5. It just is a matter of manipulation and lots of patience. And we at least have the patience, I hope. And with practice, we can get better at manipulation. So, let's try an integral. Tangent to the 4th y dy. Now, which thing should we be thinking of? If you look at this, you might say, it doesn't look like any of these. Well, they often don't. Remember, we have to manipulate. Well, which one is the best one to shoot for? And here's the philosophy. Essentially, you should think of it, notice, come to here. So, if you have an even power of tangent, you should think of that like an even power of secant, and vice versa. Because you can use that identity to rewrite them. So when I see tangent to an even power, I could say, well, I can replace it by secant to an even power. And like, ooh, that's good. So that's our idea. We're going to be focusing in on this case right here. Because we see that we can introduce secants to even powers. So let's think about what we can do. Let's use this identity, and we'll do it one time, and we'll see where we get. So tangent to the 4th y. What can we do? We can think of this as tangent squared y dy. So I'll just be careful and do a single tangent squared, becoming what? Well, tangent squared becomes secant squared minus 1. Just move that 1 across. And if we multiply this through, we get tangent squared y times secant squared y minus tangent squared y dy. And again, we're back into our situation where we have addition or subtraction. So we can treat these two integrals separately, depending upon what we want to do. So let's think about the two parts. Are we happy with this one? The answer is we're ecstatic with this one. This is beautiful. Do you see that? You got that nice power of tangent, got a secant squared. Life is good. So let's do that integral really quickly. So if we do that integral, what we would do is we said, let's let u equal tangent y, du equals secant squared y, dy, and lo and behold, this integral, this first integral becomes u squared du, which would become 1/3 u cubed plus the c, or replacing what u is, 1/3 tangent cubed y. All right? That's the first part. But of course, that's not the only part. Now we have to work on the second part. So, tangent squared. Well, what do? Well, we go back to what we just said a minute ago. If I see a tangent squared, I can make it look like secant squared. So what we're going to do here is we're going to think of this in the following way. So right now I have minus integral tangent squared. I got to work with that. But I can say, if I have a tangent squared, that's secant squared minus 1. So this is minus integral of secant squared minus 1. Or, if you like, that's really the integral of, with the minus through, 1 minus secant squared y. And now, life is good. Integral of 1 is y. Integral secant squared is tangent. Don't forget the minus. And of course, the plus c. And now we just combine these two parts together, and now we have our antiderivative. And life is good. All right, so that's good. So again, whenever you see secants and tangents going together, this is sort of the go-to identity. And remember, an even power of secant becomes an odd power of tangent and vice versa. And that lets you reduce things down. Let's talk about this difficult journey. So let's start. Remember, we know the integral of secant. So the integral of secant we can do. So let's do the integral of secant cubed. Now you might say, what about secant squared? Well, we know that one too. So secant cubed. All right. So how do you do the integral of secant cubed? Well, the answer is we don't do it right away. So we're going to think about this integral. We say to ourselves, well, what can we do? Secant, we can do that integral, but it's tough. It involves log. Secant squared. Ah, that's nice. Secant cubed, we don't know. That's what we're working on. So here's an idea, and it's not the most obvious idea. Let's think about it as really secant times secant squared. Now at this point you might be thinking, we're heading towards substitution, and the answer is no. What we're heading for is going to be integration by parts. We see secant and secant squared, and what are our parts? Well, secant squared has a beautiful integral. So this part is our dv. Secant, not a great integral, but has a decent derivative. So we'll call that our u. So we get that du will be secant times tangent. And what is v? Well, the integral of secant squared is tangent. And I forgot my dt. So, applying integration by parts once, what do we get? Well, we get the following. We're going to get uv, secant of t, tangent of t, minus the integral of v du, which is secant of t times tangent of t times another tangent of t. So if we put that together, we get secant of t, tangent squared t, dt. Now, at this point, you're probably thinking, wait a second, you said we can turn an even power of tangent into an even power of secant. So isn't tangent squared essentially the same thing as secant cubed? Kind of. Yeah, in fact, you raise a good point. That's actually a great point. Let's think about what we actually have here. So what is tangent squared? Well, we can replace tangent squared by secant squared minus 1. That's true. That's absolutely true. So what do we get? Well, this is secant of t, tangent of t, minus, if I multiply this out, there's secant times secant squared is secant cubed. And I'll write that as its own integral. Then I have secant times 1, which is secant. Now be careful with the signs here. Secant times a minus 1, but there's another minus, so plus integral of secant. And now we're like, hey, good news. This integral we can do. It's log of secant plus tangent. It's a weird integral, but we can do it. That integral we can't do. And how do we know that? Well, because we're doing it right now. And at this point, you're probably thinking, great, well, we're stuck. Actually, no. Ha 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 ha. We're about to get our answer. Because here's what we can do. If you look, you see these two secant cubed of t's? They don't actually cancel. They can combine. So we can move this across. And if we move it across, what do we have? Well, the answer is that we're going to get a secant cubed added to that secant cubed, so that 2 integral secant cubed t dt is equal to secant of t tangent of t plus this piece log of secant plus tangent, and anything else plus c. Now you might say, wait a second, where did that plus c come from? Well, remember, these two are actually not the same thing. They're the same up to some constant plus c. So that's where that plus c came from. So we're really close. In fact, what's wrong? The only thing wrong with our answer is that there shouldn't be a 2. Okay, so let's fix that. So it becomes integral secant cubed t dt, divide everything by 2. 1/2 secant t tangent t plus 1/2 natural log secant plus tangent. And then plus, now you might say 1/2 c. You wouldn't be wrong, but oftentimes we just say, look, c is a constant. Constants can absorb other constants. It's a sponge. So that 1/2 c will just replace by c. And there you go. That's the integral of secant cubed. You'll see, aha, it's kind of like integration by parts. Rearrange, life is good. Not so obvious. Not so obvious. And now, you're like, okay, well that's that journey. What if I wanted to do a higher power? All right, well, since you asked, let's do it. What's the integral of secant to the n? So a reduction. Now, reduction rule is a very fancy way of saying, find a way to relate to an easy case or a simpler case. Now you might say, well, how do we find a simpler case? The idea is, make that power smaller. So we want to take this integral of secant to the n and write it as an integral of secant but with a smaller power. So here's the idea. We're actually just going to repeat this idea over here. Just do a little careful. So the integral of secant to the n, I'll think of it as secant to the n minus 2 times secant squared. Why? Because secant squared, that's easy to integrate. That's going to be my dv. Here's my u. So what do I have? Well, I'm going to have that du is n minus 2, because I'm going to do the chain rule here, so the n minus 2 comes down, secant to the power of what? It'll be n minus 1 t, right? Because bring the power down, reduce the power by 1. Anything else? And the answer is yes, and I didn't leave myself enough space, times the derivative of secant, which is secant tangent. Or, if you rewrite this, you can write this as n minus 2. You have a secant times a secant, which makes this secant to the power n minus 1 times secant to the power 1. Secant, whoops, that shouldn't be n minus 1. Ha 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 ha. Right? Because I need to subtract 1. Should be n minus 3. Pay attention. Pay attention. All right. So n minus 2 t tangent t dt. All right. That's du. And then v, really simple. That's just the integral of secant squared is tangent. So we get uv. So secant to the n minus 2 t tangent t. Okay, uv minus the integral v du. So there's an n minus 2, and we're going to have secant to the n minus 2 t tangent squared t dt. And now our goal is, hey, let's replace this tangent squared t by secant squared minus 1. So the same thing we did before. So this is secant squared minus 1. So if we do that, what do we get? Well, we're going to get the secant to the n minus 2 t tangent t, okay, that first term. And I'm going to think about this as really being two pieces. So the first piece, I'll pull out, the n minus 2 comes out. Secant to the power n minus 2 times secant to the power 2 is secant to the n. And now, what else do we have? Well, we have a minus and another minus makes a plus. And n minus 2 still. And then we have integral secant to the power n minus 2 t dt. Now at this case, or rather I should say at this step, we're going to take this piece here, that's secant to the n of t, and combine it with that secant to the n of t. If we do that, how? Well, we pull it across. So I have one of them here, n minus 2 come across to join it. So what we get is we get the following. N minus 1 integral secant to the nt dt is equal to these two pieces here, secant to the n minus 2 t tangent t plus n minus 2 integral secant to the n minus 2 t dt. And finally we divide. So the integral of secant to the nt dt is equal to 1 over n minus 1 secant to the power n minus 2 t tangent t plus n minus 2 over n minus 1 integral secant to the power n minus 2 t dt. All right, what have we done here? Well, notice what we have is the following situation. It says, hey, if I want to know the integral of secant to the n, I just need to know how to do secant to the power n minus 2. So I've gone to a smaller power. But now I can keep doing that again and again and again and again. All right? So how can we use this? Well, let's do an example like we would never, ever want to do. Okay, so brace yourself. We're going to do the integral of, let's just do secant to the 7th. Just to convince ourselves we can do it. Integral of secant to the 7th t dt. So here, we're thinking of n as being 7. So according to the rule, we're going to take 1 over n minus 1. So that's 1 over 6. Okay, so that's the 1 over n minus 1 times secant to what power? Well, n minus 2, so that's secant to the 5th t tangent t plus, now we come here, we want n minus 2 over n minus 1. So n minus 2 is 5 over 6 integral secant to the 5th t dt. Now we say, okay, fantastic. Instead of having to do secant to the 7th, we have to do secant to the 5th. So we come here and we say, okay, let's apply the rule with n equals 5. So this becomes the 1/6 still stays there, secant to the 5th t, tangent t, plus 5/6. I'm going to put a parenthesis here. Remember, parentheses save points. We want all the points. So n equals 5. So we have 1/4, because 1 over 5 minus 1, secant to the power 3, secant cubed t, tangent t, plus n minus 2 over n minus 1. So remember, we're at n equals 5, so 5 minus 2 would be 3. 5 minus 1, 4. So 3/4. And that's going to be the integral of secant cubed t dt. So let's multiply this out. So we get 1/6 secant to the 5th t tangent t plus 5 over 24 secant cubed t tangent t plus 5 over 6 times 3 over 4. Now if we do that here, we can actually clean up a little bit, because notice that 3 divides into 6. with a remainder of 2. So it'll become 5 over 8. In other words, 15 over 24 is 5 over 8. And we have the integral secant cubed t dt. Now at this point you could say, hey, let's plug in the formula. But you know what? We don't have to, because we can do the power reduction with n equals 3. So if we do that, what do we have? We've got the first two terms again. 1/6 secant to the 5th t tangent t plus 5 over 24 secant cubed t tangent t plus 5 over 8 times, parentheses, because remember, parentheses save points. How? Because remember that the 5/6 multiplied through, right? So we want to make sure the 5/8 multiplies through. So we're doing n equals 3, so it's 1 over 2 secant to the 1, so that's just secant, tangent t plus 3 minus 2 is 1 over 2, so 1 over 2 integral secant t dt. And now we're good, because this is an integral we can actually do. Log of secant plus tangent. Good. So what do we get? We get, okay, we don't need that power reduction anymore. So we get our answer. 1/6 secant to the 5th t tangent t plus 5 over 24 secant cubed t tangent t plus, here we go, 5 over 8 times a half is 5 over 16 secant t tangent t, and 5 over 8 times a half is again 5 over 16 log of secant plus tangent, and of course plus c. Now, we've taken the journey for 7. You can imagine you can do this for 7 or 9 or 11. Good news, good news. You do not have to memorize this formula. You do have to be able to integrate secant cubed. So you can either memorize the formula for secant cubed. I don't recommend it. I say just do the process and you'll find the answer. It should be easier to remember the process. But this just shows you how a power reduction formula works. And the idea of power reduction is actually a fairly common idea. It just says, if I'm trying to understand something, let me reduce to a simpler case. Because simpler cases are, as they say, simpler, and hence the name. So it's a good idea to sort of adopt the philosophy. How can I take the problem I'm currently working on and make it a simpler one? All right, well, that brings us to sort of our last idea for today. Find the integral of something in the form sine of ax, sine of bx. Of course, there's other things. You could have sine, cosine, cosine, cosine. Now, for these, you need identities. And I'm going to tell you right now, we are not going to expect you to know these identities. So these are identities that allow you, sometimes they're called sum to product, product to sum. But they essentially say, lo and behold, I can take a product of two sine functions, and I can write it as a combination of two cosine functions. Now, we care about these things because, again, in the future, as you go further on, you're going to see that trig functions are your go-to things when it comes to modeling periodic things. And so what happens if we multiply two things which are periodic? Well, we have to understand what happens when we integrate something that looks like this. So when you get to that point, almost always you'll have your identities handy. So we're not expecting you to memorize these identities, just know how to use them. So let's just do an example to illustrate. Sine of 2 theta, cosine of 4 theta. So what do we have? Well, notice that these don't match. And whenever you have the insides aren't matching, you have to do something. So when you see something doesn't match, you know automatically that means there's a trig identity that has to come into play. Don't try to integrate trig functions where you have two different insides. It's not going to work. You have to manipulate. Now, you might say, okay, couldn't we do something like double angle formula, get this cosine 4 theta in terms of sine squared and cosine squared, and then do all sorts of crazy stuff? And the answer is absolutely you could. and you would get the correct answer. But in this case, we want to use one of these formulas. So we say, okay, we have here a sine times a cosine. So that means the correct one to use is the following. And in particular, what I'm going to do is I'm going to move this 2 across. I'm going to think of, what do I have here? Well, I'm going to think of this 2 as being the A, and this 4 as being my B. So according to the rule, this is the integral of sine of A minus B. So 2 minus 4x plus sine of A plus B, so that's 2 plus 4x all over 2 dx. Now, what do we have? Well, this is sine of minus 2x plus sine of 6x all over 2. Let's take a moment to clean it up. Notice that we have a minus here inside of the sine function. Now, sine is an odd function. Now, that's just a way of saying I can pull the minus out of the sine function, because remember, sine is odd, so minus on the inside can be moved to the outside. Cosine, on the other hand, is even, so minus on the inside, just get rid of it. Plus sine of 6x. And now we're ready to integrate. So the integral of sine is negative cosine. Well, there's already a negative on this one, so that integral will be cosine of 2x. We need to say what goes in front. Well, because of the 2 on the inside, it will be a half, but there's another 2 already there, so there's 2 halves, making that a fourth. Here, integral of sine is negative cosine, so negative cosine 6x. What goes in front? Well, because of the 6, we've got to divide by a 6. There's already a half, so we put those together. That's 1/12. And then plus c. So that's how we can apply those types of identities. And again, if you get to a situation where you need these identities, we'll give them to you, which is a way of saying we'll almost never give you those types of situations. All right, well, we've done a lot today. Let's do a couple problems just sort of to help us cool down. It's been a hard day. We should do a little bit of a cool down. Suppose we have the following. Let's find the integral 0 to pi over 4 of sine of 2 theta cosine squared theta d theta. Now, let's talk about what we need to do. You might say, isn't this a problem like what we just did? So if you went back to what we literally just did, you'll see it doesn't fit the mold. Why not? Because see how there's a sine and a cosine squared. This is when you have sine sine or sine cosine or cosine cosine. So no, we can't use these identities. It won't work. What else do you notice? Let's point something else out. Remember what we said? If they don't match, you got to use a trig identity. Well, why do we point that out? What do you see here? You'll see there's a 2 theta versus just theta. 2 theta and theta don't match, which means we have to use a trig identity before we do anything else. Because if they're not compatible, nothing will work. So we have to change one of these two. Now, which one do we change? And the answer is whichever one we want. So we could go in 2 different directions. One direction is we could say, well, let's change this sine 2 theta. We can use double angle. 2 sine theta cosine theta times cosine squared theta d theta. And if we do that, we're actually pretty happy. Why? Because we see sine and a cosine cubed. This is very much like one we just did a little while ago. So we can say, okay, so this is 0 to pi fourths, cosine cubed theta, put the 2 out in front, sine theta d theta. We can say, all right, let u equal cosine theta. du would be negative sine theta d theta. We can move the negative across, and we get, well, put it in 0, cosine of 0 is 1. Put in pi fourths, cosine of pi fourths is root 2 over 2. So just updating the bounds. Then we're going to get 2. Then we're going to get u cubed and then a minus du, because we've got to account for the minus sign. Well, that's not a hard integral to do. The integral of u cubed is u to the fourth divided by 4. So we have to divide 2 by 4, which is a half. Don't forget the minus. So minus 1/2 u to the fourth, evaluated from 1 to root 2 over 2. So that's minus a half. And if you take root 2 over 2 and take it to the fourth power, well, let's just square it first. That would be 2/4, which is a half, squared again. You get 1/4, and then minus 1 to the fourth, that's minus 1. So we get minus 1/2 times minus 3/4, which is 3/8, and that's our answer. Now remember I said there were 2 routes you could take. What's the other one you could have taken? Well, the other way you could have taken and said, look, don't do the sine to theta, do power reduction. So I can say 0 to pi fourths, this is sine of 2 theta, then cosine squared becomes 1 plus cosine 2 theta over 2. And now we're happy because they're both the same inside. So both are 2 theta on the inside. So this is, I can pull the 1/2 out, and then I have 0 to pi fourths sine of 2 theta plus sine of 2 theta cosine 2 theta. Now, here, there's lots of ways to integrate it, but I like to do the thing that says power reduction again. I can combine these together as sine of, not 1/4, 1/2, sine of twice that angle, 4 theta. All right, so I can think of this as integral 0 to pi fourths of 1/2 sine of 2 theta, and a half times a half, 1/4 sine of 4 theta, and d theta. So if we did that, well, we can just integrate. So integral of sine is cosine. So 1/4 cosine of 2 theta, okay, a half, and then divided by 2 on the inside, plus 1/16 sine of 4 theta. Not sine, sorry. Integral of sine. All right. It's been a long lecture, right? Okay, so let's be careful here. Integral of sine is not cosine. It should have been negative cosine. This is why you always double check your work. So this is not plus, it's minus. There we go. And there is a cosine there. Okay, but that's fine. That's fine. It's not a definite integral. We don't need a plus c, but we do need to evaluate 0 to pi fourths. So let's see what happens. All right. Well, I'm getting kind of nervous here. I hope I get 3/8 out. If not, don't tell anybody. Shh, our secret. Okay. So plug in pi fourths. 2 times pi fourths is pi halves. True story. Cosine of pi halves is 0. So we get 0. Plug in pi fourths here. You get cosine of pi, which is negative 1. So that'll become negative 1 times negative 1 over 16, which is plus 1 over 16. Then we're going to subtract, plug in 0. Cosine of 0 is 1, so that's minus 1/4. And then here, cosine of 0 is still 1, minus 1/16. Minus goes through as plus. So what do we have? We have 1/4 plus 1/16 plus 1/16. Well, common denominator, let's just put everything over 16. We get 1 plus 4 plus 1 over 16, also known as 6 over 16, or 3 over 8. Yes, so it does work. Again, there are more than one ways. Be careful. Be careful. Don't want to make a mistake. All right, let's do a few more. The more practice we do, the better we get. If you're happy, you don't have to go all the way to the end. All right, let's do another one. Suppose we have the following. Suppose we had the integral of tangent to the 5th theta secant squared theta d theta. Now, what do we do? Well, we have options, right? Whenever we see combinations of tangents and secants, there's 2 things you want. Well, one thing you want is to say, hey, I can think of this as just something involving just tangent, for example, tangent to the fifth times a secant squared. And now, this is good, because I can make a substitution. U equals tangent, du equals secant squared theta. And if we did that, we say, oh, this is like u to the fifth du, which gives us 1/6 u to the sixth plus c, or 1/6 tangent to the sixth theta plus c. All right? But it might be possible that we can't do that, or that we could say, hey, what if we can do something else? What is something else? So our goal is to really think of this as stuff. In particular, I'll think of this as secant theta tangent to the fourth theta times secant tangent, right? Because if you look, we have the right things. We still have 2 secants, so that's our secant squared. We still have 5 tangents. Now, this would be great if I can write everything here in terms of secant. And tangent to the fourth says that that's possible. Because remember, even powers of tangents can become even powers of secants. That's our nice trig identity. So, what would this become? Well, this would become integral of secant theta. So tangent to the fourth, I'm going to think of that as tangent squared squared. All right? We'll build our way up to it. Secant theta, tangent theta, d theta. All right, let's just remember this is our answer. All right, so this becomes integral secant theta times tangent squared becomes secant squared minus 1 squared times secant theta tangent theta d theta. And now we're happy. Only secants and then the derivative of secant. So we're ready to do our substitution. U equals secant theta du equals secant theta tangent theta d theta. So what do we get? We get integral, we get u times u squared minus 1 squared du. All right, well, that's not impossible. Now, there's lots of ways you could do this. You could actually do a substitution here, or you could expand. If we expanded, well, what would we get? We'd get u to the fourth minus 2u squared plus 1. Then multiply that u through. So this would become integral u to the fifth minus 2u cubed plus u du. And now integrate each piece. So that's 1/6 u to the sixth minus 2 u to the fourth over 4 plus u squared over 2. And out of c. And we're not done. We've got our substitute u. And remember, we're doing our secant substitution now. So this is 1/6 secant to the sixth. 2 over 4 is 1/2 secant to the fourth plus 1/2 secant squared plus c. Now, you might be saying the answers don't match. That's not necessarily a bad thing, because with trig identities, there's 1,000,001 trig identities. They don't always have to match. But what we mean by that is that they are equivalent up to various trig identities. Now, I want to do one last thing, and I promise this one truly will be the last one. And we don't even have to really work it all the way out. But I want to look at it, because I think there's something important here. What if you saw the following integral? So the integral of cosine to the fifth t over sine cubed t dt. And you ask yourself, what can you do? Well, I want to point something out here, because there is something kind of cool going on if you look. How do we think of this power of sine? And the answer is, that's an odd power. It really is sine to the minus 3. So, when we look at these, we say, wait a second, cosine's to an odd power, sine's to an odd power, which means we really have choices. Now, what are our two choices? Well, our two choices are the following. One choice is to say, let's pull off a single cosine to the n. So cosine to the fourth t, sine cubed t times a cosine t dt. And at this point, we say, okay, rewrite everything in terms of sine. So we want to have this expression just in terms of sine. Well, that's not so bad, because cosine to the fourth, I think of that as cosine squared, and then I say, all right, that cosine squared, I can replace that by 1 minus sine squared over the sine cubed cosine t dt. Now at this point, we say life is good, because I can say let's let u equal sine t, du becomes cosine t dt, and what we end up with is that this becomes 1 minus u squared over u cubed du. So, forget where it came from. 1 minus u squared over u cubed. What do? Well, the answer is break it up into parts. 1 over u cubed minus u squared over u cubed du. Or, you can write this as 1 over u cubed minus 1 over u du. And now, life is good. The integral of 1 over u cubed, which probably we should have written it as u to the negative 3. But okay, integral of u to the negative 3, well, that would be u to the negative 2 times the reciprocal of negative 2, which is minus a half. Integral of 1 over u is log u. So we end up with minus 1 over 2 times u squared, but u is sine, so 2 sine squared minus log sine t, and then, of course, plus c. Okay? So there's our answer. It wasn't so bad. But remember, we said both powers were odd. So what could we have done? Well, the answer is, the other thing we could have done is said, let's pull off a single sine. So I want a sine t up here. Now, what's the power downstairs? It won't be sine squared. What will it be? It's going to be sine to the fourth. Now, at this point, we can do the same thing we did here, which is say, look, I want to write everything in terms of cosine, because then that becomes my derivative of cosine. So I'm going to skip the intermediate step, and I'll just rewrite what it is. So it's going to become cosine to the fifth t over 1 minus cosine squared t squared sine t dt. And if you let u equal cosine, du equals negative sine dt. And so if you were to keep going, and for some reason I really want to, the punchline is about to reveal itself. You get minus u to the fifth over 1 minus u squared, quantity squared, du. Now, here is the punchline, why I point this out. I'm not going to keep going with this, because this is hard. What makes it hard? Notice what happened over here. When I come back to this part, there was a minus sign, but where was it at? Oh my gosh, I did this side wrong. Did you see my mistake? Okay, let's fix it. Where was my mistake? Do you see it? I forgot that square. See, that should have been squared there. It should have been squared there. Which means that this is actually the integral of 1 minus 2u squared plus u to the fourth over u cubed du, which is equal to u to the minus 3 minus 2 over u plus u du. And so we end up with minus 1/2 u to the minus 2 log u plus u squared over 2 plus c. So that's minus 1/2. Put a sine squared downstairs. Minus 2 log of sine plus 1/2 sine squared plus c. There we go. All right. But other than my stupid mistake, where is the algebra? You'll notice that as a consequence, where are these signs? the plus and minus. They're happening in the numerator. Look over here. What's going to happen? Where is that? It's in the denominator. Plus signs in the numerator are awesome. We love it because it lets us say, pull things apart. Plus signs in the denominator are terrible. They're hard to deal with because they don't break up so nicely. It would be wonderful if there was a way to do it, and we're going to learn it, but it's harder to work with. So when you're thinking about how to simplify problems, keep in mind that you want to make sure you move in a direction where things are going to be nice. And when you have a choice, put your plus and minus signs in your numerator, because otherwise life gets tough. And we don't want that. We want life to be good. All right. Well, thanks for letting me go for so long. Hope you have a good day, and we'll see you next time. Bye.